Why, hello! We're back once again. You should have prepared my space a little better. Anyway. Howdy. We're back to Sudoku time. Very, very good. You know how it is. It's rat run. What else is it gonna be at this point? Speaking of that, I would like to do more Sudoku puzzles. I did, like, in the past, record a few Sudoku puzzles that weren't rat run. And I mean, soon enough, in 4 weeks' time, the rat run puzzles are gonna run out once again, phase 2. I don't know if there's been any, word on if there's a phase 3 in the plans. I don't know. I don't want to assume anything. So, I was thinking about it, and yeah, I think I will try to do a few more, like, diverse puzzles. I think that would be fun. But for now, let's do this. This, by the way, is a 4-star difficulty. This is the second rat run puzzle that is 4 stars. Yeah. Which might mean this video is going to take a while. Or I'm just not going to be able to solve this, in which case you're not really hearing this. And I'll try again in the future. But, let's do it. So, the order of the rules here is a little weird, actually. I guess because they can't say normal Sudoku rules apply. So, sort of normal Sudoku rules apply. Let's read the rules here. So, Schrodinger cells. Fill each row, column, and box with the digits 0 to 9 once each. Oh, but there's only 9 squares. How are you going to do that? To make this possible, each row, column, and box contains one Schrodinger cell, which contains 2 digits. The value of a Schrodinger cell is equal to the sum of the 2 digits. So, in normal Sudoku, we'd have to put the digits 1 through 9 in each row, column, and 3x3 box, which you can see in this puzzle delineated by these dotted lines, since we have a bunch of other lines here for the eventual maze part of the puzzle. But in here, we actually have to put the digits 0 to 9. So we're going to have something like 1, 2, 3, 4, maybe 9 there, 8, 6 there, a 0 there, a 7 there, and then which digits are left? 5 and 8. So that could mean, for example, that this cell is both a 5 and an 8, which we can't really mark that well. We're going to mark it with, like, it being a certain color, probably, and then two pencil marks there to mark what the value of that cell is. So that's going to be interesting. Aim of the experiment. Finks the rat must reach the cupcake by finding a path through the maze. The path must not visit any cell more than once, cross itself, or pass through any thick maze walls. As well as moving orthogonally, Finks may move diagonally if there's a 2x2 space in which to do so, but may never pass diagonally through a round wall spot on the corner of the cell. So the goal of this puzzle, other than doing Sudoku, this weird Schrodinger Sudoku, is going to be finding a path for Finks, the rat here, to get to the cupcake. So she might do some loops, might do something weird, or she might get to the cupcake like that. And what she can do, as we've read here, is that she can move diagonally, so she could do that. That's completely allowed. What is not allowed is for her to do something, whoopsie, that's definitely not allowed, is for her to do, is for her to do something like this. She can't do that because she'd be passing through a round wall spot, and that's no good. Now, other rules. Black currents. Values, 2 values separated by a black current have a 1 to 2 ratio. So that's simple, right? These are what we normally call crop key dots. If this was a 2, this would be forced to be a 1 or a 4, because the digits in the black dots need to have a 1 to 2 ratio. That's pretty simple. One-way doors. Finks may only pass directly through a purple arrow in the direction it is pointing. Purple arrow always points to the smaller of the two digits it says between. So if Finks was somehow here, and she wanted to go down, she could. But if she was instead over here, and she wanted to go up through here, that's not allowed. And also, this has to be higher than that, this has to be higher than that. That's pretty self-explanatory. And finally, test constraint was the second weird rule of this puzzle, because the first one's going to be these Schrodinger cells, but in this experiment, dotted box borders divide the correct path into segments. The values of two adjacent cells within the same segment always have the same difference. And this difference is unique for each segment. E.g., if a segment has a difference of values 1, 3, 5, 7, then its same difference is 2. And so no other segment may have the same difference of 2. Well, that's complicated. So let's say, somewhere in the path would do something like that. So whatever digit that is, let's say it's a 3, then the difference between this digit and that digit, let's say this is a 5, has to be the difference between this digit and that digit. So that would be forced to be a 7. Now, I say that would be forced to be a 7, knowing full well that we also have to account for these weirdo Schrodinger cells. So that would have a value of 7, yes, but it could be something like a Schrodinger cell containing both a 1 and a 6. That would work, because the values would go 3, 5, 7, and that would be the same difference of 2. So what I'm basically saying is that these rules are going to work very weirdly with each other. We even have a little space here for notes. I don't know really how I'm going to use these, but we'll see if I need to use them at all. But yeah, let's get started. I was looking at this puzzle yesterday, and unfortunately my brain started thinking. And you know that there's only danger when that happens. And I thought, the first thing I thought is, well, this beginning is pretty simple, right? Finks the rat is gonna be forced to do that. She's absolutely gonna have to do that, otherwise she can't get out of this box. And then the other thing I thought about is that, hold on, she's crossing all 9 of these cells. So what same difference here would work? And, well, I was thinking definitely not anything 5 or higher, because, and this kind of gets into completely different Sudoku rules, but if you have a same difference of 5 or higher, there's numbers that just can't be paired up with anything. For example, 5, right? If you had the same difference of 5, somewhere on this line, there's going to be, well, let's not talk about Schrodinger cells yet, okay? Let me just pretend for a second that Schrodinger cells aren't a part of this puzzle. So somewhere on this line, there would be a 5. Well then, what would you put on either side of it? You couldn't put anything, right? Because if you went 5 under 5, you would get to 0. If you went 5 above 5, you get to 10. Now, again, that is actually possible because of Schrodinger cells, but bear with me for a moment. And then I started thinking, okay, so if Schrodinger cells weren't a thing in this puzzle, would this be... actually, shouldn't delete that. Would this be forced to have a same difference of 1? And definitely for sure. Because we don't only care that the differences are right, we care that their order is also correct, right? So it's not just the fact that, anything 5 or higher for same difference would not be possible because some digits can't be paired up. Is the fact that anything 2 or higher is impossible because you couldn't fit everything on the line, right? Because if this was the lowest digit possible, if it was a 1, and you had a same difference of 2 on this line, then you would go 1, 3, 5, 7, 9, and now what? Technically, you can't actually get to an 11 because of Schrodinger cells, but you couldn't continue. These 3 definitely couldn't be filled. The same thing would happen if you started with a 9. You go 7, 3, or 7, 5, 3, 1, and then you're stuck. So my thought is that this definitely has a same difference of 1. But the problem is, I actually don't know what digits I can place here. Because, well, first things first, the same difference might be going up or it might be going down. But the other thing is that the same difference might start at 0 and go to 8. It might start at 1 and go to 9. So, again, ignoring the fact that Schrodinger cells exist for a moment, you could go 1, 2, 3, 4, 5, 6, 7, 8, 9, or you could go 0, 1, 2, 3, 4, 5, 6, 7, 8. And those would both work. Now, I suspect that now allowing myself to think about Schrodinger cells is going to somehow make that make a little more sense. 1 second. Just turn the lights on. My bad. Cause, well, okay. Well, one thing I can say for sure... Actually, let me... Yeah, okay. What I'm thinking of right now is... Must the Schrodinger cell in this box be some number paired up with a 0? Because if it isn't, then either we have a digit that's above 9, or a value that's above 9, which I don't think is going to work. Yeah, because if we have a value above 9, the only thing that might work is 10 if we went 2 to 10, but then that's just not going to work, because 1 and 0 still have to be, somewhere in the line. I don't know if I'm explaining myself very well. I don't think I am. How do I explain this? Okay, well, here's a thought. Schrodinger cells are weird, but the one saving grace is that there's only one of them per box. So there's only one of them per, segment of the line. Same different segments. So they can only make any one line very slightly weirder than it would normally be if you were talking about just regular Sudoku. A line can't be completely bonkers, right? It can't go 8, 10, 12. That can't happen, right? Only one very weird value can appear per line. Now, if the very weird value here was 10, it would be made up of one digit above 5 and one digit below 5. So you're using up 2 of the digits, from that range to get to 10. But if you're at 10, say if this cell had a value of 10, and we have the same difference of 1, then we would go 9, 8, 7, 6, 5, 4, 3, 2. But where does 0 go? 0 definitely doesn't go there, because we can't pair a 0 with a 10 to get to 10. So 0 would have to go somewhere, and it just can't. So all that to say, the same difference set here is definitely either 1 to 9 or 0 to 8. And the reason I'm now thinking it's not 0 to 8 is where do you put the 9, right? There has to be a 9 somewhere. Even if it's in a Schrodinger cell, that cell is going to have a value of at least 9. It's impossible to have only values 8 or lower in an entire box. So what we're looking for is definitely either 9, 8, 7, 6, 5, 4, 3, 2, 1, or 1, 2, 3, 4, 5, 6, 7, 8, 9. Which means none of these cells have a value of 0, which then means the 0 must be paired up with something to create a Schrodinger cell. Now, the only problem is I don't think I can say what that something is. And I'm pretty sure it could actually be any of the cells, because 0 doesn't change the value of the cell. That's the only problem with pairing 0 up with something, is that you don't really get any more information. It's as if it was a completely normal Sudoku box at that point. But one thing I know is that if we're going up or down, if we're going up, the values in the cells are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we're going down, it's 9, 8, 7, 6, 5, 4, 3, 2, 1. That always has a value of 5. Now, I don't know if it's a digit 5 or if it's a 0 paired up with a 5. But I definitely know 5 is there. Now, how am I going to mark that? I guess what I can do... Let me think about this. Okay, so I'm gonna write a 5 in there for now. And I'm gonna color it, let's say purple, right? So purple is gonna be the color of... Actually, no, let's not do that. Let me do this instead. So red is gonna be the color of... This is a Schrodinger cell. That's gonna be important for when we actually find one, because then, since there is the restriction here that there's only one per row, column, and box, actually finding a Schrodinger cell is going to do a lot of good work in locating other Schrodinger cells. But, so red-white is going to be, this might be a Schrodinger cell. So that 5 there means that there's definitely a 5 in that box, but it might be together with a 0. Now the other thing is that these are a 1-9 pair, and either of them could contain a 0. These are 2-8 pair, and either of them could contain a 0. These are 3-7, and these are a 4-6. And again, any of these could contain the 0. So for now, I am going to do this, even though that's really... that's really, like... ugly, honestly. That's really ugly, but it's going to help me think. I think. So, I think that's all we can do in this box for now. I don't think we can get any more information about which way the sequence goes, or where the 0 is. I think we're gonna have to do more stuff to figure out more about that box. I've recorded for 20 minutes already? Okay, let's speed it up a little bit. Another thing that I thought about yesterday is how long can a same difference sequence be? And not that long. So this one was 9 cells long, sure, but that's because the same difference was 1. Now, what if the same difference is 2? Let's start at the lowest value we have, 0. And let's go up by 2. Well, we'd get 0, 2, 4, 8. And then it's actually possible to make a 10, right? So you could have something like 0, 2, 4... That even works with the crop, 8, 4, 6, 8. And then this cell could be a 3 and a 7 together in a Schrodinger cell. So that would go 0, 2, 4, 8, 0, 2, 4, 6, 8, 10. That's only 6 cells. And again, like I said, the one saving grace is that there's only one Schrodinger cell per box. So you can only have one very weird value per box. Now, if I think about that in... Yeah, if I think about that in odd numbers, it also doesn't work. Because it could have something like 1, 3, 5, 7, 9, and then something here that adds up to an 11. Which you actually can't make with only even numbers, but let's just imagine that this cell has a value of 11. That would still only be 6 cells. So anywhere else in this puzzle, since we've already used the same difference of 1 in this box, the same difference is going to be at least 2. And so you can't visit more than 6 cells in one box, which means we're definitely not going this way, because that would visit 7 cells. So I think that does mean Finks is going up, which is going to give us quite a bit of stuff. Now it's actually getting interesting. Because now, this is visiting 4 cells right here already. And like we said, the maximum we can visit is 6. So we can't do this. We can't exit this box through there. Because if we did, then we'd be forced to do that, and that's already at least 7 cells. So we don't go through here. So we do go somehow through this opening, I think. We either go straight there, or we kind of meander a little bit. Now, the other question I'm having now is, since this box here has 5 cells in it at least, must it be the 2 same difference? I think... No, barely not, actually. Barely not. It could be the 3 same difference. If we had something like 0, 3, 6, 9, and then this is a 4, 8 cell, Schrodinger, then we could have 0, 3, 6, 9, 12. I don't think that works with anything above 3, is the thing. So if we go 0, 4, 8, yeah, we're already forced to use a Schrodinger cell, and we definitely can't use another one. So I think this box right here, the top left box, is going to have the same difference of either 2 or 3. Which actually does restrict this black dot right here. Because this black dot, it can't have a difference of 1, so it can't be a 1-2 pair. It can't have a difference of 4, so it can't be a 4-8 pair. So it is either a 2-4 pair or a 3-6 pair. Which is definitely something. Okay. Well, we can continue our path a little bit. We can do that. Ooh. Well, look at that. That's already 5 cells. So we're not going right here. That would be way too many cells. That would be 8. So we are going left. Now, we're not going left again, or we'd be crossing the door in the wrong way. So we are going down. But the more important thing is now this has 6 cells in it. Which, that definitely can't be a difference of 3. Definitely not. For sure no. Because, like, if we do our same trick, 0, 3, 6, 9, we're forced to use a Schrodinger here. And we can't use another one. So that right there has a difference of 2. Which means this one is left as a difference of 3. So those aren't 2 and 4. Okay. This is 4 stars. For sure. But it's actually flowing quite well so far. Now that means we can only have 5 cells in this box. So that is definitely going to happen, that connection. And the other thing that I'm thinking of is... I think we are going to be forced to... Yeah, I think we're going to be forced to do very similar to that example that I gave. Where it goes either 0, 3, 6, 9, and then a Schrodinger here. 9, 6, 3, 0, and then a Schrodinger here. And those are actually the only options. Because you can't have a Schrodinger here and then go down to a 9, because that can't be a 9. So I think that means that's a Schrodinger cell. That adds to 12. And then that's a 9630? Is that right? That's right! That's crazy. Holy crap. Okay. Well, that being a Schrodinger cell is actually huge. Because it means these 3 are not. Which actually clears up that 5. So that 5 is actually alone, which is kind of funny. But it also clears up all of these cells. So none of those are Schrodinger. None of these are Schrodinger. And none of these are Schrodinger. This don't need to be white anymore. Because, again, you can only have one Schrodinger per box, row, or column. So these two cells have to add up to 12. They can't be a 3-9 pair, because those are already used. They could be a 5-7. Well, they can't be a 5-7, because they're 5. So they are actually a 4-8 pair. So 4 and 8 are in that cell, which means this is not a 4. This is a 6. And it's actually a natural 6, because it can't be Schrodingered. Now, because that's a 6, we know what order the stuff is going, the sequence is going in. It goes 7, 8, 9, 4, 3, 2, 1. We still don't know which one of these cells is a Schrodinger, though. One of them is a Schrodinger. So if I click this, it's actually going to tell me that the puzzle's wrong. Yeah, but I don't think that's actually the case. So, playing with Schrodinger cells is actually, I think, going to force me to not use the checker, which that's going to be a new challenge. We'll just have to live with it, unfortunately. Oh, none of these are the Schrodinger. Because, again, the Schrodinger in this box has a 0 on it. And they can't have a 0 on it because of that 0, because it's Sudoku. So these aren't the Schrodinger. They are safe. Which means the Schrodinger is in this column. Which means the Schrodinger here is in this column. This column is safe. And this is... yeah, this is an interesting black dot. Because it can't have a 3, an 8, or a 4, a 3, or an 8 in it. So it must be a 1-2 pair. 1, 2... here, 1, 2 here, so 1 and 2 go there. 4 and 8 are there, which means we can actually fill these in, what's left in this box. 0, 1, 2, 3, 4. 5 and 7 are left, and 7 is definitely bigger than 5. And now I can fill in this, which is... well, again, 0 is taken. 0 is in one of these 3. Yeah. So 0, 1, 2... 3, 4, 5, this is a 6, to finish off that column. To finish off this column, we have 1 and 2 are taken, 3 is missing, 4, 5, 6, 7, 8, and 0. Okay, so 0, 3, and 9 are missing there. Which means these are... they're going to be from 4 digits, because there is a Schrodinger here, so they are from 4, 5, 7, and 8. Okay. There's no kind of restriction... yeah, there's no kind of restriction about the values in the Schrodinger cells. Like, this one has a 4 and an 8. But you could have another Schrodinger cell that has a 4 and an 8, as long as it's not in the same row, column, or box. Oh, this... black dot is interesting. It doesn't have a 4, 8, or 3. So it is also a 1-2 pair. Okay. That did a good amount of work. Again, this is going to tell me that it's wrong. But I'm pretty sure that that's correct. Now. Well, like we said, this has the same difference of 2. This little bit right here. How's that going to work? It has 6 cells in it. Which means it definitely has a Schrodinger, because if it didn't, then it couldn't have 6 cells. We could go 0, 2, 4, 6, 8, but then this would be impossible to fill. So the Schrodinger in this box is definitely in one of those 4, so it's not there. Those are safe. Oh, and I actually know exactly where it is. It has to be in one of the extremes, right? Because if it wasn't, that would just give us another value between 0 and 9, and that's not helpful, I don't think. So I think the Schrodinger cell is there. These are safe. Which means these are safe, and those are safe. Now, there's actually a few ways this could work, is the problem. Because we could go 0, 2, 4, 6, 8 Schrodinger, or we could go 1, 3, 5, 7, 9 Schrodinger. Although we can't, actually. Because that gets into the point that I was making before. If we go one, well, first off, that wouldn't work because of this, but... Wait, I broke it, didn't I? No, I didn't. Never mind. I thought I broke it, but I didn't. If we went 1, 3, 5, 7, 9, first off, that wouldn't work because of Sudoku, but it also wouldn't work because this can't be an 11, because we only have even digits left. We have 0, 2, 4, 6, and 8. And in no way can you combine two even digits, sum them together, to get an odd number in 11. So that's not going to be the case. So the case is going to be 0, 2, 4, 6, 8, and then this adds up to a 10. So it's either 1 and 9 together, or it's 3 and 7 together. Don't know which one. Either way, that's a 1, that's a 2. These are all the odd digits. So they are 1, 3, 5, 7, 9. That's not a 5. That's not a 5. That's not a 3 or a 7. That's not a 1 or a 9. That can't be a 9, because there's no digit bigger than 9. That can't be a 1, because there's no digit... Sorry, yeah, there's no digit that 1 is bigger than. That is a 5, actually, because that 1, 2 pair, my bad. So, yeah, that's not a 3, because 3 is not bigger than 9. That can't be a 3, 7, because now that would be empty. So this is a 1, 9, which means that is a 7, that is a 3. Bro, I don't know. This is actually getting filled pretty quickly. Like, the path is lacking so far, right? The path is not doing too great right now. But, again, if I'm doing things correctly, which so far I think I am, hold on. Oh, no. Okay, hold on. I actually have to delete these to check something. Okay. Woof. I just had a horrible realization. For some reason, I've only been... So, again, I said I wouldn't cheat, but unfortunately, there we go. That's just how I play Sudokus. I'm sorry. Yeah. If you don't like that, there's many other Sudoku channels. That's just how I prefer to do it. To actually know if I'm on the right track or not. But I just had a horrible realization. The black dots could have a Schrodinger cell in them. And that's probably going to happen at some point. So you could have something like an 8 here, and then a 7, 9 there, and that would be a correct black dot. Because black dots, yeah, two values separated by a black current. So far, that hasn't been the case, but we have to look out for that. Wow, I didn't even realize that. That could have been real bad. This black dot doesn't have a 2 or an 8 in it, so it is a 3, 6. Again, these are normal cells. These are fine. One of those is Schrodinger. I don't know if that's a Schrodinger, so I can't say it's a 3 or a 6. It definitely has a value of 3 or 6, but I don't know which digits are in it. This is not a 1, 2, 3, it's a 4. And this is not a 0, 1, 2, 3, 4, 5, 6, 7, or 8. That's a 9. Okay. And so the digits here, there's going to be 4 of them, are 0, 1, 2, 3, 4, 5, 7, and 8. Okay. Cool. That could have been real bad. Oh, I just thought of something. These have to have the same difference, don't they? But they must be from the digits. Yeah, okay. We can kind of just combine them and see what works. Because, for example, if the 4 and the 8 were together here, there would be a cell with a value of 12. But then you would have 5, 7, 12. That's not the same difference. How about 5 and 8? You'd have 13. Well, that would be 4, 7, 13. That's not going to work. And then if 7 and 8 were combined, you would have yeah, if 7 and 8 were combined, you'd have 15. And then it would go 4, 5, 15. That also doesn't work. What about combining 4 and 5? Well, then you'd have the values of 7, 8, 9. And that works, except for the case that we can't use a 1 difference, because we've already used it here. So that doesn't work. How about combining 5 and 7? Well, then you'd have 4, 8, 12. And that works. So, yeah, let me use my notes here, actually. So, the things that don't work, I'm going to put down here. So, 4, 8 doesn't work. 5, 8 doesn't work. And 7, 8 doesn't work. 4, 5 doesn't work. 5 and 7 works. Which one haven't I checked yet? 4, 7 doesn't work. Yeah, it doesn't work. Because 4, 7 goes... Actually. Oh no, 4, 7 does work. Well. Yeah, 4, 7 does work. Because it would go to 11. And then it would go 5, 8, 11. Which actually does work. But it doesn't. Because 5, 8, 11 has a difference of 3. And we've already used the 3 difference up here. So that doesn't work. 4, 7. And I think that's all the combinations. Yeah, that's 6 of them. 4 choose 2. Is that 6? Yeah, that's 6. Okay. So, the Schrodinger cell here is a 5, 7, adding up to a 12. And so the sequence goes 4, 8, 12. Which one thing that means is that the middle cell is a natural 8. And then the other two, one of them is a natural 4, and the other is a 5 and 7 together to make a 12. Now, a dangerous thing about that is that now we've used our 1 difference, or 2 difference, or 3 difference, and our 4 difference. So now, yeah, this is going to be really constrained. Because now, the minimum difference that 2 cells can have in the path is 5. And that's going to be really tough. So if we start at our lowest value of 0, and then go to 5, then we're immediately forced to have a Schrodinger cell. Which I think now means anything else on this path, any other, box, can only have 3 digits on the path? That's crazy. Now, one thing about that is that that's not going to get lower. Unless we have to use the same difference of 9. Unless we have to do that, then the maximum of digits that we can have per box is going to stay at 3. Because we just proved that it is 3 for 5. And we proved earlier that it's 3 for 8 as well, actually. Actually, I don't know if I proved that, but I'll just do it now. 0, 8, and then a Schrodinger with 7, 9. That works. 0, 8, 16. The only one that doesn't work for is 9, because you'd go 0, 9, and then this has to have a value of 18. And that's just not possible to do with the remaining digits. Most of these could be 7 and 8, and those combine to make 15. So if there's any same difference of 9, then it can only go through 2 cells. Otherwise, we can go through 3 cells at most. Which is quite constrained, I think. Very constrained. Very constrained. Well, that makes me think. There's 2 possible exits we can take from where we are right now. We could go directly right, and that's 3 cells, that's okay. Or we could go through here, and then, either do something like that. Please. Why does it do that? Or like that, and that's 3 cells, that's okay. Then if we end up here, we're gonna have to go out through there. And the only way of doing that in 3 cells is like that. Then we could go like straight up, that's okay. Then, okay, that's actually interesting. So again, reiterating what I said. There are, okay, that actually makes a lot of sense when I think about it. There are 2 ways I can go. Either I can go directly here, and then I come out through there, or I could go down, and then I'm going to be forced to go right, and then I'm going to be forced to go up. But once I'm here, I'm going to be in one of these 3 cells. Either way, it's not possible to make it to this box in only 3 cells. Even if I'm here and I take the shortest path, that's 4 cells. So then I'm going to be forced to exit through there. But once I do that, then this is already used up, right? Because we said this is the world where we went down. So I'm going to be forced to go up and then right. So I'm going to end up here anyway. So either way, if we directly go there or if we go here and then loop around to there, we are going to end up here. And we are going to do that. No matter what, that's going to happen. And then from here, we need to make it to the cupcake in 3 moves. So we're going to do either that or that. If we do that, then either we go 6, 9, 12, which is not going to be the case because we've already used our 3 difference, or we go 3, 9, 15, which could actually happen if that's a 7, 8 pair. So I can't say that's wrong quite yet. What I can say is wrong is this. That's not going to happen. Because if it does, this can't be a 3, definitely. Because it would go either 3, 2, 1, which we've already used our 1 difference, or 3, 1, minus 1, which, disregarding the fact that minus 1 is unmakeable in this puzzle, we've already used our 2 difference. So this would be forced to be a 6. Now, this being forced to be a 6 forces this to be a 1, because we've already used our 4 difference over here. And then this goes 6, 1, minus 4, which not going to happen. So we don't do that. We do this. And then that's forced to be a 3 because of what we said. That's a 6. And it goes 3, 9, 15. And the only way to make 15 is if this is a 7 and an 8. So that's not a 0 or a 5. That is a Schrodinger cell, adding up to 15. These are not 7 and 8, and they are safe. Okay. Are we still good? Well, we're not, because these. If I erase those, then are we good? Yeah, we're good. Please go back. Okay. So now we've used our 6 difference. So we've used, actually, yeah, that's what I use my notes for. We've used our 1 difference, or 2, or 3, or 4, and or 6. So we're missing 5. Oh! Whoa, okay, that's crazy. I just realized. Differences over 9 are possible, actually. Whoa, okay, that's crazy. Yeah. Because I was thinking, if we loop around through here, is that going to be way too many segments? But it actually won't. because we have, 5 segments. Actually, we have 6 segments done with this one. We have 1, 2, 3, 4, 5, 6. Yeah. So if these don't connect, then they are 2 separate segments. So this is going to be segment 7, then 8, 9, 10, 11. So we're going to have 1, 2, 3, 4, 1, 2, 3, 4, 5. Yeah. We're going to have 11 segments, which you might think that's very hard to do. And it's complicated, yeah, but it's possible. Because one of these could have a difference of 11. There's nothing stopping it. This could be a 0, and this could be a 2, 9 in a Schrodinger cell, and that would be a difference of 11. That's fine. The only thing is that any difference above 9, before I said that only 9 had this property, but actually it's any difference above 9 can only have 2 cells. And if it is above 9, then one of those cells is going to be forced to be a Schrodinger. With 9, that's not necessarily the case. You could have 0, 9 as digits. But with anything above, you're going to be forced to use a Schrodinger. But that is actually possible, to have a difference above 9. And I think that's what's going to happen, because this is a Marty Sears puzzle. So, I feel like that's exactly what's going to happen. Oh, this is Schrodinger, so these are safe. I should mark that. Okay, well, good work. What can we do now? Well, this is a safe cell, so it's definitely a 3. There's nothing else it could be. This doesn't have an 8, a 3, or a 6 in it, so it is from 1, 2, and 4. That is not a 1 or a 4, so it's actually forced to be a 2. Wow. Whoops. Okay. 2. By Sudoku, 2 is forced in here with either a 1 or a 4. That's not a 4. There's definitely a 2 in there, one of those 2. This is, well. I was about to say this has to be a 3-6 pair, because it can't have a 1, 2, or 4 in it, but it could have a Schrodinger cell, and then weird things could happen. This is not a 3. This is a normal pair. It doesn't have... the only thing it doesn't have is a 1 or a 2. So it could be a 4-8. Oh, it can't be a 3-6, actually, because 3 and 6 both see that square. So it is a 4-8 in that order. Which... ugh, God. Okay, I'm just going to delete these and add a 0 in there. I'm sorry. I play with checking on, okay? I'm sorry. Anyway, what was I saying? Lost my train of thought. Right. This is actually interesting, because we start at an 8 in this same difference. So one thing I can tell you is that the next cell is definitely not that one, because then it'd be a same difference of 4, and that's already used up. So the next cell is either... whoopsie daisy. Gosh darn it. The other cell... the next cell is either here, or it's there. If it's there, then we're definitely not going down, because that would require at least 2 more cells. So we are going to do that. And that's a little hard, I think, because that black dot... what's that black dot going to be? Again, if it has a Schrodinger cell in it, it could be some weird-ass stuff, right? It could be... could be what? It could go... it's going to have to go down, because it definitely doesn't go up from 8. Otherwise, the only possible thing would be 8, 9, 10, and 9 and 10 are definitely not one double the other. gonna go down. Which... No, it just doesn't work, I don't think. Yeah, it doesn't work. Yeah, it doesn't work. Because that's saying this is going to be half of that. And then this is going to be a third of that. Well, 8 divided by 3 is not an integer, I can tell you that much. Because yeah, with same difference, this would go x, 2x, 3x. But yeah, 8 is not 3 times anything useful. Thankfully, we're not dealing with fractions in this puzzle. We haven't gotten there yet. So we're not going right. So we are going here, definitely. And now, well, now we can't go directly right, because we'd be required to take at least 4 cells. So we are going directly down, which means we connect there. Now, we can only take 3 cells in this box, so we are going to have to do that, definitely. Okay, well, now this connects there, for sure. And now we're going to have to connect this to that somehow, and I don't know exactly how yet. But we'll figure it out. This difference is still hard to do, I think. I'm correct so far. I'm doing something wrong, isn't I? No, I definitely have something wrong here. Because right now, the smallest difference we can have is a 5. We can't go up from 8, because that's going to be 13, 18, and then those are 2 Schrodinger cells. But we also can't go down, because that's 8, 3, minus 2. So, wait, no, I definitely have something incorrect here. But what is it? I don't know yet. I'm confused. I can mark these, because I don't have anything better to do. 1, 4, 5, and 9. It's not a 4 or a 9. That's not a 9. That's not a 9. My bad, not 9. 1, 4, 5, and 0. Okay. That's not a 4. I think my path is correct so far. I mean, the digits are correct, so definitely I'm on the right path, but am I getting some of these differences wrong or something? 4, 8, 12. That's definitely a difference of 1. I'm missing something for sure. Let me read. Value of a Schrodinger cell is equal to the sum of its 2 digits. Right. Same difference as 2, so no other segment may have a same difference of 2. So how's this gonna work? The puzzle is broken, dude. How long have I been recording? Only 54 minutes. Yeah, it felt a little too easy, didn't it? Is it because I broke something? I mean, again, I don't see how I could have broken something, because the digits are correct. So what the heck? Let me mark these. Just because, again, I have nothing better to do with my brain right now. No, not a 1. 1 is already taken. 0, 1, 2... What's missing? 3, 5, 7, 6. That's not a 6, 7... That's not a 3, because 3 is already taken there. Four is in one of these two. So 4 is in one of these 3 by Sudoku. 3 is in there. If 3 was there, this would be forced to be a natural 6, because it can't have a value of 6. Actually, it's not forced to be a natural 6, it could be a 0, 6. Okay, maybe I should come back to thinking about this. I don't see how this works right now. Let me just try something. Okay, so I mean I can't get the puzzle wrong. It's not broken in that sense. So what the heck? Is it... yeah, I don't see what I'm doing. So, again, let me walk through my thought process again. We're not going down from here, otherwise these would have a difference of 4, and we've already used up our 4 difference over here. So we are going there or there. If we're going there, then we can't make it down here, because that would require us to take 1 cell here, and 1 cell here, and that would be 4 cells. And that's not going to happen by our rules. Yeah. So we're going to have to connect there. We're going to be forced to do that. But now, what I'm thinking is that this is definitely not going up from 8. Because if it does, these are either going to be forced to be 2 Schrodingers in the same box, or they're going to be 8, 9, 10. And 10 is not double 9. So it's going to go down. But if it goes down, then this digit is the twice of that one. But again, we have the same difference going on. So this is going to be x, 2x, 3x. 8 divided by 3 is not a number we can put in there. So we don't do that. We do this. And if we do that, then we're forced to do this. And then we're forced to do that. But now, what the heck are these digits? What are these numbers? They definitely... They contain a Schrodinger. But what I'm struggling to see is how they can not contain 2 Schrodingers. Because we have the same problem. We're not going up. Otherwise, this goes 8, 9, 10, but the difference of 1 is already taken. So this goes down, but it's not going down by a 1, 2, 3, or 4, so it's going to go down by at least 5. So this is going to be at most a 3, but if it's even a 3, then this is going to be forced to be a -2. I'm not understanding this. The puzzle's broken. I am missing something huge right now, and I don't know what it is. Is this why the puzzle's 4 stars? Is because it breaks halfway through? Again, I've only been recording for an hour. It's not like this puzzle's super long yet, but I don't know how to continue. Because it seems like it's broke. Anything I do breaks it, but somehow the digits are correct. Hold on. I have to stare at this for a second. Yeah, I don't see how this is gonna work. Is there... Oh! I got it. I understood. Same difference. Wow, okay. One, I'm really happy this hasn't come up before. Otherwise, I would have gotten even more confused. I got it. I understood. Same difference. Okay, let me just think about something really quick. Okay. We do go down there, for sure. That is correct. This cell, wait for it, is going to have a value of 8. That's how this works. Wow, that is beautiful. Holy shit. That is insane. Wow. Same difference. In this specific puzzle doesn't mean that you have a strictly increasing or decreasing sequence. I thought it did, and so far it has. But it doesn't always mean that. It just means that adjacent cells must have the same difference. So if this has some difference x going down, this could have that same difference going up. Normally, that wouldn't work, because 2 8s can't go in a box together. But in this puzzle, they can. They just have to have the same, the value of 8. So if this was a 2 6, well, it can't be, because 6 is taken. But if this was a 3 5, then it doesn't matter what this digit is. Because we go down by some number, and then we go up by that same number. That is the same difference. That works. Wow, okay. That's insane. So this cell has a value of 8. For sure. It's either a 1-7 pair, or it's a 3-5 pair. But it has a value of 8. And the only way it can have a value of 8, if there's already an 8 in the box, is if it's a Schrodinger. Which now means all these are safe. These are safe. That one is safe. Which is huge, because that means that is the 4. And then this is the 5-7 pair. This is not a 4. Wow. That caught me really off guard. That got me. I'm not gonna lie, that got me bad. I did not expect that one. Now these are normal, so they don't have a 4, 8, or 3, so they are actually a 1-2 pair now. Woof, that got me. I'm not gonna lie, that got me. There's not many things this can be, actually. Because this can't be a negative number, so it does kind of matter what the difference is. It can only be a difference of 5 or 7. If it's a difference of 5, then this is a 3. If it's a difference of 7, then this is a 1. But it's not that, because the 1's already taken. So this is a 3. Which means this is not actually a 3, 5. It is a 1, 7. That's not a 3. That's not a 1. That's not a 1. So that's a 2. That's a 1. That's not a 1. 0, 5 are taken. So that's a 1-4 pair there. Okay, wow. That's not a 3. Which means the 3 is right there. That's not a 7, because 7 is taken. That's... Did I break it again? I broke it. No, this time I actually broke it. Is that not a 3? That's not a 3. Wow. Okay, never mind. I understood this wrong. Oh. It can be a 3, a 1, or a 0 if the difference is 8. Okay, let me go by logic and figure out why it can't be a 3. It can't be a 1, obviously, because that. Now, if it's a 3, this still has to add up to 8. And it now can't be 1, 7, 2, 6, or 3, 5. Or 0, 8. So this can't be a 3. So this is actually a 0. There we go. Now this works. My bad. Look, it's a hard puzzle, okay? There's a lot to think about. Give me a break. Now this does add to... This is a 3, 5 now, to add to 8. So this is not a 3 or 5, this is not a 3, this is not a 5. This is a 0, 9 pair, so 3 is there. Alright. Wow. Anyway, the difference of 8 has now been used. Right there. Is that correct? That's correct. Okay. Woof. What digits are left in this box? We've used 0, 1, 2, 3, 4, 5, 6, 7, and 9 are left. Oh, neither of those are 7s. There you go. That's a 7. That's a 5. That's not a 5. That's not a 7. That's a 3, 6. Okay. 1, 2 have been used in this column, so these are actually pretty restricted. They're from 7 and 9. Yeah. Okay. Can that be a Schrodinger? No. No, that can't be a Schrodinger. Because if it is, its value is going to have to be 1, 2, or 4, and that's just not going to happen. The only one of those we could even make with a Schrodinger is a 4, but then we would need either... Actually, no, that might work, because we could have a 0, 4. Gosh damn it. Okay, that might be a Schrodinger still. When did we even mark that, actually? Oh, by Sudoku. We marked that by Sudoku. So this is actually wrong, what I marked there. There's a 2 in there for sure by Sudoku. But it just has to be paired up with a value of 1 or 4. Not specifically with a 1 or a 4 digit. This is a 1 or 2 because it's natural, but this could still be a Schrodinger, unfortunately. Okay. Well, okay, well, we can do a little more path. We can do that, which we did before all that fiasco happened, but whatever. This difference is a little interesting now. This can't be a 1 now. Because if it was, this would be a difference, well, actually, no, Ah! If this is a... Okay. If this is a 1, this can't be a difference of 8, because that's already used, so this would be forced to be a 6. If this is a 2, this can't be a 6, because the difference of 4 has already been used, so this would be forced to be a 9. So this is either 1, 6, or 2, 9. Those are the only options. Don't know which one. Okay. Where do we continue from here? Now it's getting hard. Now it's getting difficult, dude. Now it's getting there. Can I figure out how these connect? Maybe. Not sure. What digits are left in this column? One of them is a Schrodinger, so it's gonna be 5 digits. They are 0. Interesting. Zeros in there somewhere. Okay, hold on. They are 0, 1, 2, and 4, and... Is that it? That can't be right. It. Zero, 1, 2, 3's taken, 4, 5, 6, 7, oh, 8. Okay. None of those are 2s. That's not a 1. Well. Huh. Okay. Well, this is a little interesting now. Look at this. Yeah, look at that. That's fun. This is an odd number. And this is even. So whatever the difference between these two is, it's an odd number. And then we're going to have the same difference here. So we're going to go odd, even, odd. Well, the only way to get an odd number there is if either we have a Schrodinger with a 1, or if that's a natural 1. Either way, 1 is definitely in that cell. It might be together with something else. It might be alone, but it's definitely in there, which means it's not in here. So that's not a 2. Or that is a 2 now. That's like that. There we go. So 1 is definitely there. It's not here. This doesn't contain an 8. Definitely not. Because the value of this is now 4. But I don't know if it's a 0, 4 or if it's a 4 alone. I don't know yet. Can this be a 0? No. Maybe. Maybe. It could actually. That could be a 0, because we could have the same thing that happened here. This could be a 9, 0, and then this is a 1, 8, adding to 9. That would work. Wow. Can this be an 8? No, this can't be an 8. Can it? Together with the Schrodinger? No, it can't. Okay. Yeah, one thing I really need to understand is that if a Schrodinger cell is being put in because we need a number above 9, then it's definitely at one of the extremes of the well, that's not the case, but it's definitely at the extremes of the segment. So if this was a Schrodinger, I'm trying to explain why this can't be an 8. So it can't be an alone 8, because then this is 7 or 9. So the difference between these would be 1, and the 1 difference is already used. It can't be a 0, 8, because same problem. You know, the difference here would be 1, and it can't be a 4, 8, because then that's a 12. And then this can't, you know, how do I explain that? If this is a 12, then if this either goes 9, 12, 15, which is not going to happen, 9, 12, 9, which isn't going to happen, 7, 12, 7, which is not going to happen, or 7, 12, 17, which is not going to happen. So basically, this is not an 8, which leaves the only cell that can be an 8 in this box as that one. But the 1 is also there, so this is a 1, 8 pair. There we go. This is not a 0 or 4. This is a 1, 8 pair. It is a Schrodinger, which means that one's not a Schrodinger, so it's actually a natural 3. Wow. Okay, those aren't Schrodingers. These two aren't Schrodingers. That is natural, so it is a 4. That's a 0. And this does go 9, 0, 9, like we said. Okay, cool. That can't be a 0 anymore, so that is a natural 4. And then that is the Schrodinger, and it is a 0 together with an 8. So now that's not a 0, that's not a 4. 1, 5 pair, but it's a 0 here and a 4 here. Very good. That's a 9 now, that's a 0, that's a 6, 9. This is our difference of 7, so we have used difference of 9 now, and we've used our difference of 7. That's all of them, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. That's all the differences we've used so far. Whew, these two cells, what are they? They are 0 and 9. Yeah. What is left in this row? It's 3, 6, and 7. These aren't Schrodingers, because that's Schrodinger. So there is a Schrodinger in there. and it contains a 7. Is that right? That is right, wow. How is that gonna work? The Schrodinger in there contains a 7. But it's on a black dot? Am I doing something wrong? Again? Hold on. Let me just mark some cells so I can think about that a little more. These are 4 and 9 in that order. They have a difference of 5, so there goes our difference of 5. That's a 0. That's a 0. That's a 9. That's a 5. That's a 0. These have to be. Yeah, these have to be natural because that is a Schrodinger. So there's a Schrodinger there, and there's a Schrodinger there, and those are the last Schrodingers in the puzzle. But what I'm wondering is how the heck can this have a 7 and be a Schrodinger? Because either that means its value, the value of the Schrodinger cell here is 13, which is definitely not going to fit on a black dot, or it's 10, which could fit on the black dot, but we've already used our 5. Something's wrong. Let me do a little more marking. This is 1, 2, and whoops. This is 1, 2, and 3. No, it's not. Yeah, 3 is already used. My bad. 4, 5, 6, 7. This is 1, 2, and 8. This is 1, 2, 5, and 7. That's not a 5. This can't. This has to have a difference of at least 10. Which means this is absolutely a Schrodinger. Which means that's our last Schrodinger. Which means these are safe. Oh. Go back. Yeah, okay. I'm dumb, dude. I literally just missed the pencil mark. That also has an 8 in it. That makes things a lot easier. Because now, this can be a 6-8, and that can be a 7. There you go. So that's a 7. That's a 6-8 Schrodinger. That means that's a 3. That's a 6. That's not a 7. These are 1, 5, and 3. The 3 goes there. 3 doesn't go there. 7 doesn't go there. Blah. Alright, we're almost done. Oh my god. This is a Schrodinger cell. It contains 2 of these digits. But the difference between these 2 cells... I feel like I'm breaking the puzzle. Well, here's one thing. The difference between this cell and whatever it goes to has to be at least 10, so it definitely goes there. And that's our difference of 14. So there's a difference of 14. Wonderful. But now how the heck is this difference going to work? Does it? I'm losing my mind. Is there a difference of 7 anywhere? Or is that a remnant of... No, there's a difference of 7. It's right there. There's a difference of 5. There's a difference of 6. Let me just make sure that these notes that I took are correct. So 1 is there, 2 is there, 3 is there, 4 is there, 5 is there, 6 is here, 7 is here, 8 is here, 9 is here, 14 is here. Am I just missing a pencil mark? Again? It's very likely at this point. That's not an 8, because that's a 6, 8. So that's a 1, 2 pair, means that's a 5. That's a 1. That's a 5. That's not a 5. 1, 2 pair makes that a 7. One, two pair makes that an 8. How's this right? It doesn't seem right. Did I fuck up my path somehow? Because this isn't right. Oh my god! It's a difference of 0. I've actually lost it. I've actually... He's too good. He's too good at making puzzles, dude. He's too good at making puzzles. Someone has to stop him. Someone has to stop him, dude. Oh my god. I felt like I lost my mind like 18 different times during that. Oh my god. Oh my god. Oh my god. Oh my god. I'm astounded that I even solved that. Again, even with cheating. Which, again, I've explained it before. I don't really see that as cheating, but whatever. Wow. Putting a difference of 0 at the end is insane. That's actually like psychopathic behavior. Not holy crap. I'm joking, of course. That's a joke for legal reasons. But that is insane, dude. Holy crap. Wow. That's crazy. Oh my god. Experiment completed successfully. Cells visited 40, black currants eaten 1. Finks performed remarkably and seemed to not even notice the added challenge. I noticed it, although she was occasionally distracted by the Schrodinger cells themselves. She paused for over a minute to inspect the double-digit cupcake, seemingly intrigued by the notion of 2 digits coming together in one cell to create a single value, before tentatively nibbling the buttercream. Good stuff. That was a tiring puzzle. That connects like that, obviously. That is a tiring puzzle, holy. And that only took 80 minutes. That didn't even take that long, but it felt so much longer than it was. Wow. I mean, I'm happy to solve that. But wow, that was difficult. There were so many moments there where, like, I felt like I was insane. I felt like I was going crazy. This was the big one. This was the big one where I thought I just lost it. Because all the digits seemed correct, but nothing seemed to work. And then I realized you can just do this back and forth thing. And then they did it again. And then we had a difference of 14 here. And then we had a difference of 0. That's not okay, dude. That's not okay. I guess we can finish our list here of differences. So all of the differences from 0 to 9, and then a 14. That's really funny. Wow. Let's see. How do we complete this? Digits not on the path in column 9. Those would be 635 0241. 635 0241. And there we go. That is Rat Run 16, Schrodinger's Rat. That's a good name. That is a good name. I'm gonna have to think of some smarter name for my YouTube video, because that is a good name. I could also just steal it. Kind of funny, but I'll think about it. Yeah, wow. Marty Sears, you absolute mad genius. Holy crap. I actually stood up when I finished that puzzle. I had to stand up because there was no way I was reacting to that. Sat down. I felt like I was going insane, for sure. But yeah, that's it. That is Rat Run 16. We have 4 more of these coming in the next few weeks. Is it? Oh, the last one, if I'm counting correctly, will come out on Christmas. Wasn't that fun? The last puzzle in this phase here is gonna come out on Christmas. That's fun. Okay. I mean, I'm probably not gonna be able to play that one immediately, like the day of, because I'm gonna have family over and stuff for Christmas. But yeah, that's it. That's the puzzle. I am tired now. I need like a nap after that. Anyway, good night.